This video is all about gear trains. How do I identify the pieces of gear trains? How do we perform calculation on gear trains? And how do we tell the difference between a simple gear train and a compound gear train? Now, when we're thinking about these gear trains, what's special, what's kind of unique about these is there's three big elements that we need to keep in mind as we transfer energy through that rotary motion, through that spinning motion that gears have. Gears are really handy to change the speed of rotation. So I can modify how many gears I have, the arrangement of those gears, is the size of those gears to change what my output speed or angular velocity is going to be. I can also put gears in or take gears out to change the direction of that rotation. And a lot of times in cars, I can change the amount of torque that is available in order to do work. So maybe I would rather value speed over torque, or maybe a little bit more of that force over the speed of my vehicle. So we're just going to dive into the ins and outs of gears, how to tell them apart, how to do some calculations, and how to perform some work using compound gear trains. So I have a gear train here, and kind of the purpose of this is to transmit some of that rotary motion or that rotational motion going around, and kind of turning that into torque through these interlocking teeth. So by themselves, it's just a gear. When we have multiple gears interlocked between their teeth, then we've got a gear train. So I've got 3 gears in my gear train, and they are all relatively meshed together. Now there's 3 pieces of the gear train that we need to identify. There is the driver gear, the input, there's the idler, and there's the driven gear or the output. So let's say that I am messing with the gear on the right, and I am going to move that gear and start to rotate that on my own. So what this means for driver, idler, driven is, because I'm putting the force into this gear, this is my driver gear. Sometimes we call it our input gear, which means that this is our output gear or our driven gear. And any gears that are in the middle that are not your driven or your driver, we call the idler gear. And really the only purpose for the idler gear, kind of similar to fixed pulleys actually, is idler gears change the direction of a rotation. So what I mean by that is, if I look at the rotation of the big gear, I'm going in this direction. If I look at the direction of the idler gear, it's going in this direction. And if I'm looking at the driven gear or the output, it's going in this direction. Now, if my driver and my driven were together, my driven would not have that same direction. So the idler gear is kind of nice because it allows my driver and my driven gear to both rotate in the same direction if that's something that we need. Now notice there's a big difference between the speed of these objects. So as I rotate the big guy, the driven gear is going really fast. So for the most part, the bigger your gear is, the lower your RPM. The smaller your gear is, the bigger your RPM, the faster you go. Now let's kind of flip this on its head. Let's say that I want to input my force into this gear. So because I am inputting my force into this little guy, this is now my driver or my input. This is my driven or my output. And this is still my idler gear. Now, before we actually perform calculations regarding gear trains, there's a few extra things that we need to know, especially the variables, because they can look kind of weird and there's some new ideas that are inputted in there. So there are 4 new variables that we need to keep in mind. There's number of teeth, diameter, angular velocity, and torque. So number of teeth we always write as N, and we can either count out the number of teeth that are on the gear itself, or Project Lead the Way also has a quick little printout if you're using the VEX parts to count how many teeth there are. We also have the diameter, which is the overall diameter of the gears themselves. That one's pretty straightforward. But angular velocity is a little bit different. So angular velocity is that curvy kind of W, and that is the lowercase Greek letter omega. And angular velocity is similar to linear velocity in that we're talking about speed, but because we have an object that's rotating around, we characterize that with angular velocity. And we always measure that in RPM, rotations or revolutions per minute. So if you think about linear speed or linear velocity in meters per second, miles per hour, the same idea for things that are rotating around is your angular velocity in revolutions or rotations per minute. Now, the fourth kind of new variable that we need to talk about is the torque. And we can relate that pretty closely to force to a certain extent for objects that are rotating around. So the more torque you have, you usually hear that with cars especially, we can somewhat relate that to force, even though that's not exactly appropriate. And for torque, we're going to use the lowercase Greek letter tau to represent that T for torque. Now, in addition to those variables, we also have the subscripts of in and out. And those represent, are we putting our energy into one of those gears and getting it out? We can think about it as input versus output. We can think about it as driver or driven. So if we're looking for the number of teeth for the input gear, we would write that as N subscript IN. If we're looking for the angular velocity of the output, we would do lowercase omega, or that squiggly w, subscript out. So now that we know the variables, let's talk about the really, really important gear ratio equation. Now, gear ratio is really similar to mechanical advantage, but specifically for gears. So this does not work for our inclined planes or our wheel and axles. This is only for simple and compound gear trains. And if you look at the equation itself, it's a big equation. But what's super useful about that is I can pick and choose which pieces of the equation I want to use. So let's say I identify all my knowns and unknowns, and I find that I have a lot of information about angular velocities. I don't have any teeth information or diameter information or torque information, and I need to find gear ratio. What I can do is I can pull gear ratio, I can pull angular velocity out of that equation, and set them equal to each other to calculate the value that I'm looking for. Now, maybe I have another equation where I don't have gear ratio, I don't have angular velocity, but I do have a lot of diameter information and tooth information. I could set an equation to have our teeth equal to the diameter ratio. So we can pick apart any piece of this equation and set it equal to each other, which makes our job a lot easier. Now, notice in the equations, the angular velocity seems like it's flipped. And that is the trade-off similar to mechanical advantage, where in mechanical advantage, the higher your force output, the lower your distance, or the less force you have to put in, the greater you have to pull it. Same idea happens for gear ratio, where if you have something with a very high angular velocity, your torque is going to go down. So notice how those are flipped in the equation. So if we flip-flop that, if we have something with a really, really high torque, then the angular velocity is going to go down. So we need to make a decision on if we want a lot of torque or rotational force, or if we want a lot of rotational speed. So now that we've talked about the parts of a gear train, we talked about some variables, some basic equations, now it's time to actually do some calculations. So let's calculate the gear ratio between the two meshed gears A and B. And if we look in the picture, it looks like we don't have diameter information, we don't have angular velocity, we don't have torque, we have tooth information. So gear A has 20 teeth, gear B has 12 teeth. So looking at our equation, I'm going to pull out gear ratio, since that's what we're looking for, and I'm going to use the N in and N out, which is the teeth portion of that equation. So gear ratio is equal to number of teeth in my output divided by number of teeth in my input. So if A is my driver or my input, then if we're focusing down on those two, B must be my output. Now, in the grand scheme of the whole gear train, B and C are both idlers, but if we're focused on A and B, A is my input, B is my output. So I'm going to toss in their teeth, and we get a value of 0.6 for my gear ratio. Now let's do the same thing for gear B and C. So if I'm focusing on those two in particular, B is my input because that's where the force is coming from. C is my output. So I'm going to plug those values in, 5 for my out, 12 for my in, and we get a value of 0.42. Now, last but not least, let's check out C and D. Same idea. C is our input now. D is our output. And if I plug my numbers in, I get a gear ratio of 4. So when we have that gear train, what we can do to find the overall gear ratio is take all of those values and I can multiply them together. So I can take the gear ratio between A and B times the ratio between B and C times the ratio between C and D, and I come up with a value of 1. Okay, a little underwhelming, but all right. So that is our total gear train ratio. Now let me show you a little shortcut that we can do for this as well. Let's imagine that we had A and D connected together. So B and C, those two idler gears, are completely gone. Just for kicks and giggles, let's figure out what the gear ratio is going to be between A and D. So I'm going to identify A as my driver or my input. I'm going to identify D as my driven or my output. And I'm going to toss in their number of teeth, which is 20 over 20 and 1. Interesting. So the purpose of that is to note that for a simple gear train, when those gears are connected in a line, the idler gears don't affect the gear ratio. Again, only for simple gear trains. So if you had a gear train of 1,000 gears and I told you to figure out the gear ratio, all you need is information from the driver and the driven, the first and the last, and that's it. We don't care about any of those idlers. Again, the only thing that the idlers do really is they change the direction of the motion for a simple gear train. Now, if we modified it a little bit and we were looking for the total gear ratio, if D had 20 teeth, the driven had 40 teeth, we could do kind of the same thing if we really wanted to, or we can make our lives way, way, way easier and have our number of teeth input, which is 20, and our number of teeth output, which is 40, to get a gear ratio of 2 to 1. So when we're doing those calculations, remember, we don't care about idler gears in our calculations. We only need the gear ratio as if the first and the last gear were meshed together. So that is for a simple gear train. When all of our gears are aligned in a row, let's look at what a compound gear train might look like. So we're going to put some of these gears in place and kind of let them spin for a sec. So we've got our first gear. We're going to mesh these two together. So right now, this is a simple gear train because we have them arranged essentially in a line. But what we're going to do next is I'm going to stick this blue gear on top of the yellow gear. I'm going to connect them on the same drive shaft so that they're rotating at the same speed. So now we have a compound gear train because now we have different layers of gears meshed and stacked on top of each other. Now let's take that last big red one and I'm going to connect it to my blue one. And here we have a great example of a compound gear train. We're no longer just a simple nice line. We have stacks of gears on top of each other. And the calculations are going to look a little bit different. So notice the ones in the middle, the ones that are stacked on top of each other, are moving at the exact same speed. One really nice thing about compound gear trains is we can get a lot of torque out of compound gear trains. So if we look at the red one, we have a very slow speed, which means we have a high amount of torque. So instead of just combining the green and the red, we can use a compound gear train to get a whole heck of a lot of torque to do whatever we need to do essentially. So let's do kind of a similar calculation, but for a gear train, or excuse me, a compound gear train. Now, my big tip for this is your calculation should only include those gears that are meshed together, not on the same drive shaft, but meshed together. So I see A and B meshed together, and I see C and D meshed together. I'm not doing any calculations between B and C because they're just rotating at the same speed together. So let's calculate the gear ratio between A and B to start off with. So my input is going to be the green one, 10 teeth, and my output, or B, is going to be that 40 teeth. That's my N out. So I find I have a gear ratio of 4 between A and B. I'm skipping any gear ratio between B and C because they are not meshed together. But I do want to find the gear ratio between gears C and D. So let's go ahead and do that according to kind of the direction of my force. My input is going to be C. My output is going to be D. So I can make sure that my calculation looks similar to that. So we have a gear ratio of 2.5. So now, the gear ratio of the entire gear train is going to be 4 times 2.5, which makes 10. So that is really important, that when you're dealing with compound gear trains, you are only performing calculations on those that are meshed together, like A and B, and separately C and D, and you are multiplying those together just like you would for a simple gear train.